In this video, we are going to study infinite limits. We're also going to use what we learned about infinite limits from the right and the left to tell us information about vertical asymptotes. So consider this function, f of x is equal to 3 over x minus 2. Our knowledge of pre-calculus tells us that that function has a vertical asymptote at x is equal to 2. So we can see that the denominator would be 0 when x is equal to 2, and that factor does not cancel out in the numerator. What we are interested in is what is happening to the function then as we approach that vertical asymptote from the left and from the right. So let's start with what happens as x approaches 2 from the right. So as x approaches 2 from the right, I'm going to be on the graph moving into 2 from the right side, and we can see that the graph is shooting up towards positive infinity. Similarly, here in the table, these are values of x that are approaching 2 from the right, and look at what the y values are doing. They're going from 6 to 30 to 300 to 3000. They're increasing without bound. So as we approach 2 from the right, the function is approaching infinity. Similarly, if we come in and approach 2 from the left, so I'm talking about now what is happening as we approach the vertical asymptote from the left side of the graph, this is now shooting downwards to negative infinity. We can see that on the graph, and we can also see that in this table. As we plug in values of x that get closer to 2 from the left, we see that these y values are shooting down towards negative infinity. So we formally write this behavior as the limit as x approaches 2 from the right of this function. That was positive infinity. As we approached 2 from the right, we went up towards positive infinity. And as we approached 2 from the left of this rational function, we went down to negative infinity. Right there. And the formal definition here, when we have a limit that's either increasing or decreasing without bound, and all increasing or decreasing without bound means is it's going off to positive infinity or negative infinity, that is called an infinite limit. So example 1, we have a function given to us, and we want to determine the limit as we approach the vertical asymptote of that function from the right and from the left. So here's our graph. Let's start with the limit as x approaches 1 from the right. So that means we need to get on the graph on the right side of the graph. So I'm going to get on the graph right here or here, doesn't matter, but I need to be moving towards 1. 1 is right there. So when I get on the graph and I start moving towards 1, we're shooting down towards negative infinity. So the limit as x approaches 1 from the right of the function f of x, or in here you could put the actual function, negative 1 over x minus 1, is equal to negative infinity. Now let's see what happens as we get on the graph and approach 1 from the left. So this time I'm going to get on the left side of the graph and move towards 1. 1 is right there. As we do that, we are shooting up towards positive infinity. So we have now seen 2 examples where we approached vertical asymptotes from the left and from the right, and our answers were positive infinity, or negative infinity, positive infinity, some combination of those. Generally speaking, when you're working with vertical asymptotes, that's exactly what's going to happen. You could have vertical asymptotes that come in and act like that, where both the limit from the left and the right would be positive infinity. You could also have vertical asymptotes where both the limit from the left and the right would be negative infinity. That's also possible. But what's definitely going to happen is as you approach a vertical asymptote from the right or the left, one of those limits is going to be infinity or negative infinity. That is the definition of a vertical asymptote. So in this class, when we are asked to show that something is a vertical asymptote, we need to show that the limit as x approaches that function, that x value where you claim the vertical asymptote is, from the left and the right is positive or negative infinity. The next theorem that we have gives us another way to show where a function would have a vertical asymptote. If we have a rational function like this, and we are able to show that there is some x value for which the numerator is not 0, but the denominator is 0, then that would give us a vertical asymptote. So just a quick example here, at this function, f of x is equal to negative 1 over x minus 1. If we plug in 1, the numerator would still be negative 1, and the denominator would be 0. So things where we have a non-zero number over a 0 number would give us a vertical asymptote. Example 2, we're being asked to find the vertical asymptotes of this rational function. I'm going to begin with a little bit of algebra and factor the denominator, because the denominator is where we look for vertical asymptotes. The numerator cannot be factored. So looking at the denominator, I can see that we have vertical asymptotes at x is equal to negative 1. We can also see that on the graph, and at x is equal to positive 1. To show that x is equal to negative 1 is a vertical asymptote, I need to consider the limit as x approaches negative 1 from the left of this function, and the limit as x approaches negative 1 from the right of this function. In order to show that something is a vertical asymptote, we need to be able to say that as we approach from the left and the right, that the function's shooting up or down to positive or negative infinity. And as we approach negative 1 from the left, the graph is shooting up to positive infinity. As we approach negative 1 from the right, the graph is shooting down to negative infinity. Because both of those left and right-sided limits are positive or negative infinity, therefore, there is a vertical asymptote at x is equal to negative 1. These 3 dots right there mean therefore. Now let's show that we have a vertical asymptote at x is equal to 1. To do that, we need to consider the limit as x approaches 1 from the left of this function and the limit as x approaches 1 from the right of this function. As we approach 1 from the left, our limit is negative infinity. And as we approach 1 from the right, our limit is positive infinity. Because both the left and the right side limits were positive or negative infinity, we have a vertical asymptote at x is equal to 1. The last thing that we're going to discuss in this lecture are properties of infinite limits, and then we're going to look at some examples where we use those properties to calculate some limits. So this theorem 1.15 is very important because it's going to tell us how to handle limits that go off to positive infinity. So as we go through the properties, keep in mind that we have a function f who, as we approach some x value, it goes off to positive infinity. And we have another function g that as we approach some x value, it goes off to some real number. So this L is just a constant. Okay, that's just a constant real number. So one function goes to infinity and the other function just goes to a number. What would happen if we were to add those two functions together? Well, if we add a function that goes off to infinity and a function that goes off to a number, that's going to continue to go to infinity. If I subtract them, that would also continue to go to infinity, because notice that f is first here. So it's like I'm taking something that's infinite and I'm taking away 7. Well, that's still infinite. Keep in mind, though, that the order of which these things happen would be important. So yes, that's a subtraction rule, but it's worth noting that if I had flipped these around, that this would then go to negative infinity. Right, so this is if I'm saying the limit of something that goes to 7 minus the limit of something that goes to infinity. Well, that's going to go to infinity in the opposite direction. Let's look at these next two now. The next two now deal with multiplication. So you're multiplying something that goes off to infinity by a constant. Well, it depends on if that constant was positive or negative as to what's going to happen when you multiply them. If it was positive, you'll go to positive infinity, and if it was negative, you'll go to negative infinity. If it was less than 0, negative infinity. If it was greater than 0, positive infinity. The last property that we have tells us the limit if we're working with a quotient, and we have to pay attention to what's in the top and what's in the bottom, in particular when the denominator is the one that goes off to positive infinity. So when the denominator goes off to positive infinity and the numerator is staying constant, think of what that means. What happens as a denominator gets very, very, very large? Well, as your denominator gets large, the whole quotient goes off to 0. If you think about what happens if you take a slice of pizza and you go from sharing it with 4 people to now sharing it with 8 people and continuing to share it with more and more people. So as I continue to cut this pie, what's happening is my denominator is increasing the number of people that it's being shared with. And as that happens, the limit of the quotient is going off to 0. So now let us put these properties to work to evaluate the limits in example 3. In example 3, we have the limit as x approaches 0 of 1 plus 1 over x squared. We're going to try to apply this sum property. So let's see what is happening to each of these individually. Well, the limit as x approaches 0 of 1, just that first piece there, is equal to 1. And then let's look at the limit as x approaches 0 of 1 over x squared. So I've broken this up into just the 1 and then into the 1 over x squared. And we're going to look at these two individually. The 1 is just a constant, so that's how we know that its limit went off to just 1. If I were to try direct substitution with 1 over x squared, we would get 1 over 0, which implies that we have a vertical asymptote at x is equal to 0. Remember that theorem 1.14 said that if your numerator was not 0 and your denominator is 0, that tells you that you have a vertical asymptote. So I know there's a vertical asymptote at x equal to 0 on 1 over x squared. I'm going to go look at what the graph of 1 over x squared looks like. There's a vertical asymptote at x is equal to 0. And the parity of that 0 in the denominator is 2. So I know that both ends of the graph go the same way. So the graph looks like this. As we approach from the left, we go up to positive infinity. As we approach from the right, we go up to positive infinity. And so as we approach 0, we go off to positive infinity. So we now have broken it up into a sum where one piece is constant and the other piece goes to positive infinity. Well, theorem 1.15 just told us if one piece is constant and the other goes off to positive infinity and you add them together, then your limit is equal to positive infinity. So we had to show that one piece was constant and another piece went off to positive infinity before we could use this part of the theorem to include that our answer was positive infinity. So this justifies that through that theorem. Now let's look at example 3b. I want to try to see if we can match this to the quotient one. So I would expect from just following the logic here that this answer is going to be 0. But in order to show that, we have to show that the numerator went to something constant and that the denominator went to infinity. So let's look at these two limits individually. The limit as x approaches 1 from the left of the numerator, well, I can just do direct substitution on that, right? X squared plus 1 is just a parabola. It has no vertical asymptotes, no issues, nothing like that. So this limit simply goes off to 2 from direct substitution, substituting in 1. It doesn't matter that it's coming in from the left. It would still be 1 if it were coming in from the right, because x squared plus 1 doesn't have a domain issue. On the other hand, the limit as x approaches 1 from the left of cotangent pi x, we need to give it a little bit of thought, because cotangent pi x does have vertical asymptotes. It has a lot of vertical asymptotes. From trigonometry, we know that just cotangent has vertical asymptotes at integer multiples of pi. So with this pi right here, cotangent pi x has has vertical asymptotes at just integer multiples. Now, mind you, there is one here also at 0. So let's see now that we have the graph. What is happening as we approach 1 from the left? So going in and approaching 1 from the left, there's 1. There's the right side of 1. Here's the left side of 1. Get on the left side and approach 1. We are going down to negative infinity. So we have a limit where the numerator is going to a constant. Good. And the denominator is going to not positive infinity, right? Ours didn't go to positive infinity. Our denominator went to negative infinity. But we have a similar property for that. So this still goes to 0. It just approaches 0 from the negative side. Our last example, example 3c, we want to see what is the limit as x approaches 0 of 3 cotangent x. This is a product. We have two things being multiplied together. We do know that the limit as x approaches 0 from the right of just 3, which is a constant, is 3. Now let's see, what is the limit as x approaches 0 from the right of the cotangent x? So I've broken this up into two separate pieces. I've broken it up, the 3 and the cotangent. Took the limit of the 3, took the limit of the cotangent. We're going to be trying to apply one of these versions. Well, not just one of them, hopefully the first one, because our first limit 3 was positive. Let's go see what is the limit as x approaches 0 from the right of cotangent x. Mind you, this graph up here was cotangent pi x. Now I want to look at the graph of just cotangent x. Well, the graph looks very, very similar. The only difference is where the vertical asymptotes are. Now the vertical asymptotes are at integer multiples of pi. And the graph still goes in the same direction. So we have enough graphed for us to be able to determine the limit as x approaches 0 from the right. Yes, there is a vertical asymptote right there at x is equal to 0 along the y-axis. That is a vertical asymptote. The left side of it, the right side of it. Get on the right side of it and approach 0. As we do that, we go down to negative infinity. So we have the limit of a product where one is constant and the other goes to negative infinity. So that overall limit will go to negative infinity.